Welcome. In this video, we are looking at the CCNP version 8 curriculum, Enterprise, focusing on core networking. This is going to be the first of two video series. Again, this is focusing on ENCOR. Welcome. Chapter 16, Overlay Tunnels. So what we're going to be looking at is we're going to be looking at GRE-based tunnels, IPsec fundamentals, Cisco location and separation protocols, Lisp, and we're going to end it with our virtual extendable local LAN network section. Alright, so let's go ahead and jump right on in. So, our first section is our GRE, Generic Routing Encapsulation Tunnels. GRE is a tunneling protocol that provides connectivity. It does not provide encryption. So, GRE, it's used to tunnel through a firewall or through an ACL to connect to a discontinuous network. Most important applications of GRE tunnels is that they can be used to create VPNs. However, GRE tunnels are not secure. They will encapsulate layer 3 packets and will forward it through a different layer 3 or different layer 3 network, whether it be IPv4 or IPv6. The issue is confidentiality. The encryption functionality is not there. So when a router will encapsulate a packet for a GRE tunnel, it will add a new header information. This will be known as the encapsulation to that packet. I'm going to grab my pen. So here is the original packet. It will then stick in a GRE packet header and flags to engulf the original header. The new IP header information will enable the packet to be routed between the two tunnel endpoints without inspection of the payload being the original content. When the packet reaches the remote tunnel, the GRE header will be removed, de-encapsulation, and the original packet will be forwarded to the router. Again, basic VPN without encryption. Again, the GRE tunnel supports IPv4 and IPv6 addressing, and it doesn't really regard what layer 2 technology is being used. So the underlining or overlaying network really doesn't matter as long as connectivity between both sides work. So here we have an example of two networks. We have router 1, we have router 2, and we have some form of ISP network. Well, the interesting part here is we are building a GRE tunnel between R1 and R2 through the ISP's network. So we can see we have a static route, and we can see the destination of our static route. So here we are actually on R1. I'm assuming this interface right here. We are forwarding everything out the 1064.1.2 network, and that is this guy right here. So how do we build our tunnel configuration? Step 1, we create the tunnel interface by using the global configuration command, interface tunnel, then you give it a number. And again, we'll have a lab walking through the steps as well. That's coming up in a separate video. Step 2 will identify the local source of the tunnel by using the interface parameters, looking at the tunnel source, and that will be the IP address and interface ID. Or the interface ID, not both. The tunnel source can be a physical interface or a loopback interface. Step 3, identify the destination and include the appropriate interface parameters, and you'll be doing that through the tunnel destination IP command. Step 4 will allocate an address to the tunnel interface by using the IP address command, and would be treating it like a physical interface, like any other interface, even though it's going to be a tunnel-based interface. The next steps are all optional, but we can define bandwidth, we can specify keep alive, and we can also define maximum transmission rate, or the MTU, for our different sizes. So here is how we would configure it on R1 and R2. You'll notice first things first, we have a tunnel interface. We assign bandwidth, an address, an MTU, a keep alive, and then we do our tunnel source and our tunnel destination. From there, on the remote side, we do the exact same thing. interface, bandwidth, address. We set up the appropriate MTU. We set up the keep alive tunnel source and tunnel destination. And from there, we can look at and build out our networks. So with this configuration between R1 and R2, it will become a direct OSPF neighbor through the tunnel. So it will ignore the network between the ISPs. This tunnel is created between both R1 and R2, and it will treat it like a local connection. If we want to see it, make sure it's live, we can do a show interface tunnel, and you should be able to see the tunnel is up, it's functioning, and if there are any issues with it. Additional commands to verify the status could be things like IP route, could be trace route. You're going to start noticing we have OSPF O, but we also now have an IA. IA is our inner areas. And again, trace route always works. So what happens if there's problems? So recursive routing and outbound interface selections are two of the more common issues when we're dealing with our tunnels or our overlay networks. So recursive routing can occur when the transport network is advertised into the same routing protocol that runs on the overlaying network. So the routers will detect recursive routes and will generate a syslog message that we've already seen in the CCNA material. Recursive routing problems are remediated by preventing the tunnel endpoints from the appropriate address from being advertised across the tunnel network. So what ends up happening is, if there are two routes, same source and destination, it doesn't know if it's going to be sending it through the tunnel or through the internet. That becomes a recursive routing problem. The goal here is you want to funnel the appropriate routed traffic through the appropriate routed port. And here the appropriate routed port would be the GRE tunnel interface. And we make that clear when we do the configuration for our GRE. So let's go ahead and move on to our IPsec fundamentals. Again, IPsec is the framework or an open standard for creating a more secure VPN. Essentially, IPsec builds the encryption portion of our VPN. IPsec will provide the security services and peer-to-peer authentication, confidentiality or encryption, the data integrity, hashing, and the replay detection that we're going to be expecting from our VPNs. So our IPsec security services are things like peer authentication, confidentiality, integrity, and replay detection. So if we are looking at peer authentication, we could be using digital certificates or PSKs. For our data confidentiality, that's going to be our encryption. We're looking at AES or SILs. However, it can also use older technologies like DES or triple DES. Don't use those. Data integrity helps prevent our man-in-the-middle based attacks, and it's going to be using the hash message authentication code, HMAC. And here we're looking at using our weaker MD5 algorithm or our more secure SHA-1. However, both of these are pretty weak, so do keep that in mind. Our replay detection, again, prevents our man-in-the-middle based attacks. And basically with our IPsec, every packet's going to be marked with a specific sequence number. That way the VPN device can keep track of our sequences as we are sending data. When we are looking at our IPsec, we can look at it in terms of which IPsec portion that we're going to handle first. And so that means looking at the packet header. We have two ways of doing this. We could look at the authentication header, and this is going to be the authentication that will ensure that the original data packet before the encapsulation hasn't been modified. This will not encrypt the entire payload. This only looks at the authentication header. If we need protection, if we need security, we're going to have to look at the ESP or the encapsulating security payload. ESP will ensure the original payload maintains data confidentiality by encrypting the payload and then adding a new set of header during the transport across a public network. We can either pick from AH or from ESP. And we have a few other portions. We can also do our different traditional modes. We have a tunnel mode and we have a transport mode. Our tunnel mode will encrypt the entire original packet and add a new set of IPsec headers. They are basically, these new headers are used to route the packet and also provide an overlay function. However, it doesn't really do encryption. Our transport mode will encrypt and authenticate only the packet payload. This mode does not provide overlaid function and routes based off the original IP header. So this really depends on what are we trying to accomplish. Our tunnel mode will encrypt the entire packet, including the new the header, and provides new header information. The transport mode will encrypt and authenticate only the payload, not the header. So it really all depends, what are we trying to do. Our tunnel mode, you'll notice, will encrypt the most, where the transport mode only does the header and the original data. So if we're looking at what is going to provide the most security, we'd be looking at our tunnel mode. However, this does use additional resources. If we're looking at what type of encryption can we do, it can do DES, triple DES, AES, and it can do SIL. SIL's not here, but we found out in our CCNA material looking at IPsec, SIL is probably one of the more secure aspects. DES and triple DES should not be used. You need to do AES or greater. AES is a symmetric encryption algorithm, and it does 128-bit keys, 192-bit keys, or 256-bit keys. After we've chose our encryption or confidentiality, we can have the ability to look at our integrity keys. And our integrity keys are going to be things like our MD5 or our SHA. MD5 is the weaker of the two. SHA is the more secure of the two. After that, we have the ability to deal with our peer authentication. I don't like the way that this is done because these two are integrity. These two are peer authentication, either through a pre-shared key or through a signature. And last, after you've done the peer authentication, then you can do your Diffie-Hellman section. And our DH is about key exchange. So I don't like the fact that they did this out of order. Normally you look at our IPsec protocol header, then you look at confidentiality, integrity, peer authentication, and then del hyphae at the very end. So we have a few different types of transform set rules. So if we're looking at the authentication header only, and again this is only allowed once, we could be looking at AHMD5 HMAC, AH SHA HMAC, or we could do a SHA 256, SHA 384, SHA 256, and so forth. These are the different types of modes that we can do. And again, this is authentication header only. If we want to encrypt our entire packet, that's going to be our ESP. And again, only one is allowed. So you could be doing ESP with AES, ESP with our generic encryption algorithm. We could do AES 192, AES 256. Our AES could also use our DES or triple DES, or we could use SIL. You'll notice it's now here, even though on the previous screen. So realistically, you're looking at AES or SIL as our encryption mechanism for the more secure options. If we want to do our AES authentication transform, again, you're going to choose either ESP MD5 or ESP SHA. You're going to choose one or the other. If we're doing some form of compression, we could also do comp-is. So that brings us back to our Diffie-Hellman, our key exchange, our IKE. What does that mean? So our IKE is actually known as Internet Key Exchange. This is the protocol that performs authentication between the two endpoints to establish the security association, the SA. This is also known as our IKE tunnel. We have two versions of IKE, IKE v1, IKE v2. There's other modes, but these are the more common of them. We have a Internet Security Association Key Management Protocol, ISAKMP. This provides the framework for the authentication and the key exchange between our two peers. This basically allows us to build, establish, modify, and tear down the appropriate security associations using our EIC modes. For the Cisco platform, EIC is the analogy to our ISAKMPs, and the other two terms are going to be used interchangeably throughout this material. When we are building a VPN tunnel, there are two main phases. Phase 1, this will establish a bidirectional SA between the two EIC peers. This is known as the ISAKMP Security Association. Because the SA is bidirectional, once it's established, either peer may initiate or renegotiate for Phase 2. Phase 2 is the establishment of the unidirectional IPsec SAs, and this will leverage the appropriate establishment of Phase 1. Phase 2 is where you can actually start sending data. If Phase 2 does not complete, the tunnel net is not actually up. Phase 1 negotiation can occur using a few different types of mode: main mode or aggressive mode. So this is what's really interesting. If we're dealing with a Cisco device and a non-Cisco device, you have to be careful what type of mode you're using, because some can handle aggressive, some cannot. I do a lot of ubiquity equipment. And so if I'm tunneling between a Cisco device and a ubiquity piece of equipment, I'm using main mode, because that's what provides the VPN of Phase 1 and Phase 2 between those two brands to function correctly. So again, when you're doing your different modes for Phase 1, it all depends on the end device and what they can support. So the peer that will initiate the appropriate SA process is known as the initiator. The other end will be the responder. So whoever initiates Phase 1, initiator, whoever is responding is going to be the responder. Main mode has several different types of messages that they can exchange. M1 through M6. Basically, M1 is the first message containing the proposal. M2 is the responder's response. M3 is the initiator's key exchange. M4 is the responder of its own key. M5 is the initiator start the authentication by sending the peer's address. M6 is the responder sending back an acknowledgement of that similar packet and authentication. And then at that point, the key should be exchanged and the tunnel should be established. If we're talking the aggressive mode has three main messages. And basically in this message, the initiator will send all the information containing an MM1 through 3 and MM5. In AM2, basically that's going to be MM2, 4, and 6. And then it will respond with AM3, which is the authentication that will be using MM5. Again, aggressive mode consists of just the three messages, and this is helping to cut down on the negotiation between our peers. However, it doesn't offer the same level of encryption provided by our MM, and this will identify of the use of the two peers used to establish the security association between them. Be careful of the end devices. If you're using two Cisco devices, you can do MM or you can do AM. If you're doing a Cisco device and another brand, you have to pay attention to which mode they can operate in. After we've done our Phase 1, we have to worry about our Phase 2 session establishment. There are a few different ways to do this. Through IPsec SAs, we have what's known as the quick mode, or QM. The quick mode will use a three-message exchange, QM1, 2, and 3. With QM1, the initiator can start multiple IPsec SAs into a single exchange method. With QM2, this message from the responder has to match the appropriate IPsec parameters. QM3, after the QM2 message has been received, there should be two unidirectional IPsec SAs between the two peers. Also in Phase 2, we have what's known as the perfect forward secrecy, or PFS function or parameter. This is an additional function for Phase 2 that is recommended but not always optional, because if it's required the additional DH exchange that will consume additional CPU cycles. The goal of this function is to create greater resistance to crypto attacks and maintain privacy. Again, all of this would depend on your end device. I have a ubiquity that requires the use of PFS. With it not on, data is not passed. So it really all depends on source and destination devices. If you're using two Cisco devices, as long as they match on both sides, you are good. However, if you're not using two Cisco devices, then you have to use that consideration. So moving on, we have our IKE. We already talked about IKE having two versions, 1 and version 2. Version 2 is an evolution of IKE 1 that will include the exchange and improvements of some of the issues. In IKE 2, communication consists of request and responses paired called exchanges, and are sometimes just called request-response pairs. There are two main types. We have an IKE SA, a niche. This will negotiate cryptography algorithms, exchange nonce, and it will perform our appropriate DH exchange. This exchange is equivalent to IKE's V1 using MM1 through MM4. Our IKE auth will actually be very similar to MM5 to MM6, as well as QM1 and QM2. Basically, if we're using MM1, or if we're using main mode, then we're using IKE V1. And again, all of that's going to be dependent on your end devices. It takes a total of 4 messages to bring up a bidirectional IKE SA and the unidirectional IPsec SAs, as opposed to 6 messages exchanged with IKE V1. So again, it really just depends on how you're trying to build your tunnel and the level of security that you want there, as well as the hardware in between. The hardware actually being the endpoints. So the differences between IKE 1 and IKE 2. IKE 1 has our main mode, aggressive mode, our quick mode. IKE 2 has our security association and our IKE auth. Maximum number of messages, there could be between 6 and 9 with IKE V1. There are 4 using IKE V2. Different methods, PSK on both, certificates on both, but IKE V2 also uses our ECC for digital certificates, where our IKE V1 does not. Differences continue with our generation and cryptography. You'll notice that IKE V1 doesn't support any of our next generation, where IKE V2 does. Our attack protection is pretty similar to both. However, IKE V2 also has additional levels of protection for our DDoS protection. So, in previous material, we talked about IPsec VPN-based tunnels being a site-to-site or remote VPN. Those are the two main categories of tunnels. However, Cisco allows us to dive a little deeper with our IPsec VPN tunnels, being a site-to-site VPN or a LAN-to-LAN. We could have a Cisco Dynamic Multipoint VPN or DMVPN. This basically allows us to use a GRE connection, and we modify that to be called a multi-point GRE tunnel, and we use that with IPsec so that we can have our encryption. We also have what's called a GET VPN, and that would be the Group Encrypted Transport VPN. This was developed specifically for enterprises to build a any-to-any tunnelless VPN, and this was to work over our MPLS. Cisco also has a Flex VPN, and this will interpretation of the IKE V2 standard, featuring a unified VPN solution that combines both site-to-site and remote, as well as other technologies like hub and spoke, spoke-to-spoke, and partial mesh directions. Lastly, we have our remote VPN access. That will be our VPN access using secured connections and our different types of technologies. It will support our iOS with FlexVPN. However, it's only using IKE V2, and you can use it on our ASA-based firewalls as well as our firepower walls. Firepower firewalls. So how do we configure IPsec VPNs? One, we have a lab walking us through this as well, but step 1, you configure a crypto ACL to classify to match the traffic. That should be an extended ACL. Step 2, configure the appropriate ISAK-MP policy for our IKE SAs. And you'd be setting the encryption, the hash, the authentication, and then the groups. Notice earlier when I said the order matters, encryption, our hash, our authentication between our peers, and then lastly our Diffie-Hellman groups. 14 is the lowest you should use. 19 and above uses ECC, and this will use a newer level of encryptography. More often than not, I'm using between 14 and 16, so it really just depends. Also, the keyword priority will uniquely identify the IKE policy and assign a priority to the policy where 1 is the highest level priority if you chose that. So that's step 1, that's step 2. Step 3 will be configure the pre-shared key by using the appropriate command. Step 4 will be creating a transform set and enter transform set configuration. Step 5 will be configuring a crypto map and enter the crypto map configuration. And you'd be again doing a ACL to match the addresses, set the peers, set the transform set. And lastly, you'd be applying a crypto map to the outside interface by using the appropriate crypto map command. Again, we have a lab walking us through these steps. That way we can reinforce our steps. I hate when they give us steps like this because they really don't allow us to hit home what we are going to be accomplishing. Here we can see the steps using a pre-shared key. You'll notice we have a crypto map. We have our crypto ISAK-MP policies. We have the initial setup. We have our crypto key association. We have our crypto IP section. We have our mode sets. We have the appropriate ACL. We have our mapping. We have our interfaces. We have our VPN interfaces, both on R1 and on R2. We can verify this by doing a show interface, looking at OSP, looking at route. That's assuming that we've set up OSPF and route. Or we can do our show crypto, either show crypto ISAK-MP SA or show crypto IPsec SA. Those are our two big crypto show commands, and they should be able to see our tunnel function if the tunnel is up. If we want to be able to verify the VTI over an IPsec tunnel, we would be looking at show interface, show crypto ISAK-MP SA, or show crypto IPsec SA. Similar commands. So that's it. So moving on, we have our Cisco Location ID Separation Protocol known as LISP. So with the rapid growth of the default free zones, the DFZs, this is also known as the Internet Routing Table. This has led to the development of Cisco to do the Cisco Location ID Separation Protocol, LISP. LISP is a routing architecture and a data and a control plane protocol that was created to handle the address routing scalability issues of the internets. If you dove pretty deep in our BGP and our advanced BGP section, you should know that there are some scalability issues of routing on the internet since BGP is the main protocol. However, that's the protocol that's always been used. So there are major issues with scalability on internet-based devices. All right, so key LISP architecture components. We have an endpoint identifier, an EID. Basically, this will be the address of the endpoint with the LISP site. And the same IP address is used today on endpoints, either IPv4 or IPv6, and they operate in the same manner, essentially. We have the LISP site. This is the name of the site where the LISP router and EID will reside. We have our ingress tunnel, and we have an egress tunnel. These are basically the LISP routers that the encapsulation packets will be coming from our EIDs, either destined outside or inside the network, again depending egress versus ingress. We also have a tunnel router, and this will refer to the routers that will perform our ITRs and our ETRs. We also have a proxy ITR, and that's known as a PITR. They're just like regular ingress tunnels, but this is for non-list sites that will send traffic to the appropriate EID destinations. We have proxy ERTs, we have proxy XTRs, we have our list routers, and that's going to be a router that will perform the function of any portion of the function or all of the function for our ITR, ETR, PITR, or our PETRs. A lot of acronyms that you sadly you just don't get away from. We have our routing locator, our RLOC, and this is an IPv4 or IPv6 address of the egress that will be facing the internet. We have a map server and a map resolver. The map server basically is a network device, normally a layer 3 device, that will learn the EID to prefix mapping entries for our egress routes. For our map resolver, this is a network device, again, typically a layer 3 device, that will receive the appropriate lists and encapsulated map requests from inbound or ingress TRs, and they'll find the appropriate ETRs to answer those requests by consulting the appropriate map server. We have a map server, map resolver, and this is when the MS and MR functions are implemented on the same device, and that means instead of calling them a map server and map resolver, they're now a map server, map resolver. We have our list architecture, and again, that basically means we have a list that will separate the IP addresses into endpoint identifiers and the appropriate routing locators. So unlike in traditional IP routing, the endpoints can roam from a site to site, and the only thing that can change is their routing locator. The EIDs will remain the same. So our list control plane, basically at this point, the control plane will operate in a very similar manner to DNS. Just as DNS can resolve a domain name to an address, list can resolve an EID into a routing locator by sending the appropriate map request to the map resolvers. And so here we can look at our list data plane. If we're looking at an ingress tunnel router, the list encapsulation packet will be received from a EID, and in an outer IP, it will use an UDP header with the appropriate source and destination address as the resource locator. In other words, they will perform an IP to IP UDP encapsulation. How do we ensure that when an endpoint with a list site is trying to communicate to other endpoints outside the list network, how can we confirm that this is all functioning? Step 1, the endpoint in list site will send a DNS request to resolve the IP address to the endpoint list site. Step 2, the ITR will receive the packet from the host 1 destined to the source, and it will use the FIB lookup to equivalate the packet according to the appropriate configured rules. Step 3, the ITR will send the encapsulated map request to the map resolver. Because the map resolver and map server functionality is configured on the same device, the MS map database system will forward the appropriate map request to the authoritative source, basically the source of truth, for the ETRs. Step 5, the ETR will send the ITR a map reply message. This will include the appropriate EID to RLOC mapping. The last step will basically allow the ITRs to install the EID to RLOC mapping to its local map cache, and it will program the FIB to forward the traffic accordingly. I really wish we had labs covering our LSP, but at this time there are no real major labs, but this is something that I think makes more sense, configuring it so that we can see step-by-step the functionality. I'll see if I can put together a lab on this material as well. So the following steps will describe the encapsulation and de-encapsulation process. So here we have our ITR will receive a packet from an EID destined to our remote network. The ITR will perform a FIB lookup. If it finds a match, it will encapsulate the EID packet and add the appropriate header. Then it will pass it along. The ETR will receive the encapsulated packet, and then it will de-encapsulate it and forward it appropriately. For our proxy ETRs, again, same similar steps. We're looking at a host will perform a DNS lookup. It will get the appropriate response. It will then send the address to the ITR to do a map request of the map request or the map responder. The map database system will respond with the negative map reply. Will include a calculated non-list prefix for the ITR and to add it to the map cache as well as the FIB. Step 4, the ITR can now start sending the appropriate list of encapsulated packets to the proxy ETRs. Last step is the proxy ETRs will de-encapsulate the traffic and send it appropriately to the destination. If we have a proxy ingress, we will take the traffic from a domain received by the proxy ITRs destined to our internal network from our web host. The proxy ITR will send the map request to the map resolver. The map database system will forward the map request to the ETR. The ETR will send a map reply to the proxy ITRs with the appropriate EIDs to our LOC mappings. The proxy ITR's lips encapsulation will encapsulate the packet and it will start forwarding them to the appropriate ETRs. Lastly, the ETR will receive the lips encapsulated packets and will de-encapsulate them and send them back to our host as accordingly. That was a lot of ways to say how it's going to be handling our routing, essentially. Our last major topic is what's known as the Virtual Extendable Local Area Network, VXLAN. This handles our server virtualization and our network virtualization. So layer 2 networks were not designed to support hundreds of thousands of MAC addresses as well as tens of thousands of VLANs. So we had to have a new design that could do that. And that is where VXLANs are designed to address this issue as seen by the traditional layer 2 network. VXLANs are made to handle a significantly increased amount of VLANs as well as a tremendous increase in MAC addresses. We've already know that a VLAN will use a 12-bit VLAN ID, giving us about 4,000 VLANs. However, with server virtualization, this could be insufficient. So large MAC address tables are also needed due to the hundreds of thousands of VMs as well as containers attached to the network. Not just that, we have our regular layer 2 technology like STP that may block links because there are a larger number of MAC addresses that are there, as well as all of the disabled links. All of this combined is unacceptable. So ECMP is not supported. Host mobility is very difficult to implement. So all of these are major issues with our traditional legacy layer 2 based networks. Our XVLANs have a 24-bit VLAN identifier, except instead of calling them a VLAN identifier, they are called a XVLAN network identifier, VNI. This allows for 16 million segments. This can also coexist within the same infrastructure. This definitely increases the amount of VLAN possibilities that our server virtualization platforms can handle. VNI is located in the shim header that will encapsulate the original inner MAC frame originating from an endpoint. The VNI is used to provide segmentation between layer 2 and layer 3 traffic. It will also facilitate and discover a number of VNIs over underlying layer 3 technologies. This will be known as our virtual tunnel endpoints, VTEPs, and when they are used. Each VTEP has two interfaces. It has a local LAN interface. These interfaces are on the local LAN segment, and they have an IP interface. This is a core-facing network interface for our VXLANs. These IP addresses are basically used to identify the appropriate VTEPs in the network. So let's look at that from the header standpoint. There are minor differences between a layer 2 Lisp and the VXLANs in regard to the header. The Lisp fields do not port over to XVLANs, are reserved for future use. So things like the Cisco Software Defined Access, or SD access, is an example of an implementation of our XVLANs with the appropriate Lisp control planes. So here you'll notice we have our internal XVLAN, and that will give us our VNIs. They will give us our reserved portions. They will give us our MAC into our IP, the UDP encapsulation. This is all part of our overlay. With our traditional Lisp, we have our interface or instance ID, and it's all part of our Lisp headers. And that is all I had for this chapter. I'm going to be working on some lab development covering some of these materials. So we're not just talking about the steps, we can actually look at how to configure them and get them to function. We talked about GRE, we talked about functionality of GRE, as well as IPsec. That was tunnel and tunnel encryption. That talked about exchange modes. That talked about confidentiality, integrity, peer authentication, and our Diffie-Hellman type groups. We talked about our tunneling interfaces. We talked about how to configure both GRE and IPsec. We talked about Lisp in detail. And then we went ahead and we ended with our VXLAN functions. Key terms was heavily in our Lisp sections. Things like our ETRs, ITRs, our MRs, our MS, our MRs, our overlays, and our Lisp sites, as well as some of our proxy commands and our VXLANs identifiers. We looked at how to create VREs. We looked at how to do our keep alives, our ISAKMP mappings. We looked at how to set our transforms. We looked at how to set our maps. We looked at how to apply them, how to set up our tunnels, how to display and how to troubleshoot them. And that was all I had for this chapter. Questions or anything, please feel free to reach out. If you have any questions or anything, please feel free to reach out. Again, with this material, being able to ask questions and discuss some of the topics in the lecture help build long-term retention, so do not be afraid to communicate with this topic. Again, I'm here if you need anything. Thank you.